Okay, let's multiply these factors in the other order and make sure that they give us the same result. And then if this product gives us the same result, then we'll be done. Okay, so this was the formula for the inverse of a 2 by 2 matrix, which was given by the entries that I'm writing down now, A, B, C, D. So if this is your matrix A, then the theorem's claim was that this is the formula for A inverse, and we're halfway done proving that claim. We still need to show that this product also gives us the 2 by 2 identity matrix. So that's what we'll do now. And I'll just draw your attention to the fact that what you have here is a product of two matrices where the one on the left is actually a scalar multiple of another matrix. So if I were to just go back to the very first page of this section, Property 13 says that when you have that, when you have a scalar and two matrices and they're put together in any of these three fashions, each three of these quantities are equal to the other two. So we have essentially the middle one. We've got a scalar times a matrix, and then that whole matrix times another matrix. Well, let's take advantage of the fact that this can be written like this. We can multiply the two matrices first and then multiply the scalar on after. Where, just to be clear, that scalar alpha, I'm talking about this fraction 1 over AD minus BC. So I'm not going to write much for this step. All I'm going to do is just change the order in which these operations are done. It's really just a bracket shift. Even though I'm not going to write brackets for this expression. Because what we have now is the product of these two matrices, and then the result will be multiplied by this scalar. Matrix multiplication takes higher order in precedence than scalar multiplication, which is why, for example, in this notation, these brackets are important to mean technically that this scalar gets multiplied onto that matrix first. However, it just turns out that due to property 13, it doesn't matter, and we have access to all three of these forms to compute whichever one is more convenient at the time. Okay, so let's actually multiply these two matrices. So the scalar will stay out front. We've got 1 over AD minus BC. But now we're going to multiply these 2 by 2 matrices and get a 2 by 2 matrix as a result. So let's work out this entry. We have D times A and negative B times C. We've got dA minus BC. Now for the entry down here, we'll have negative CA plus AC. And then what about the entry over here? We'll have D times B minus B times D. And then for our final entry down in the bottom right corner, we'll have negative C times B plus A times D. So that's what you get if you just carefully work out the product. And I'm going to take one more step just to clean things up a little bit. Because this term here, negative CA plus AC, this is just 0. dB minus BD, this is 0 as well. And if I just rearrange the products and terms a little bit so that they all look the same, I'll get this. I'll have AD minus BC, 0, AD minus BC. So now, this is exactly what we had last time, and that's good because that's what we want. Because now when I take this scalar and I multiply it onto every entry in the matrix, the zeros won't change, but these two expressions, these two entries along the main diagonal, they're being multiplied by their reciprocal. So they turn into 1. So you have 1, 0, 0, 1. So that actually gave us the 2 by 2 identity, and that completes the proof. Because now we've checked that both products gave us the identity matrix. Okay, so let's look at a couple of examples. Oh, by the way, this little box I draw at the end of a theorem, that just indicates that the proof is complete. It just makes, you'll see that lots written in mathematics and textbooks and other people's notes. It's just a way to make it a little bit easier on the reader to just quickly scan a page and figure out how much of the page is dedicated to a proof and where the one idea stops and where the next begins. Okay, so that's the end of that. Let's do a couple of examples and put this theorem to work now. Let's just summarize, by the way. So if the matrix A, and I'll even separate this. We can leave a little bit of space up here for a remark. Just a summary of what, this is really just a statement of what the theorem just said. So if if the matrix A is given by A, B, C, D, and this product, AD minus BC, is not equal to 0, then the formula for the inverse is 1 over AD minus BC. And you can see what I'm doing here. I just take the entries on the main diagonal, flip their order, and put a negative sign on the other two entries. So that's the part we just proved, right? So if you have a 2 by 2 matrix and you compute this expression AD minus BC and you get anything else other than 0, then that matrix A is invertible, and here's a formula for its inverse. Okay, the other part of the theorem, and this is the part we didn't prove, but it is important, so I want to also write it down. So if AD minus BC is equal to 0, well, then we can't use this formula for the inverse, right? Because we would be dividing by 0 when we write down this fraction. So this won't work if AD minus BC is equal to 0, and it turns out nothing will. If AD minus BC is equal to 0, A is not invertible. In other words, its inverse does not exist. Okay, so that's just a summary of what we proved. The first part is what we proved, and the second part we didn't prove it, but I promise you that it's true. You can check it on your own if you like. Here are some examples without further ado. Okay, so I'm going to give you two matrices, and we're going to find the inverse of each one, if possible. So the first one, we have the matrix A, and it's given by this 2 by 2 matrix, 6, 1, 5, and 2. And then our second example will be the matrix B, and it's going to be given by -1, 2, 3, -6. So let's tackle these one at a time. So the first one, well, let's first work out this expression up here, right? We want to know, is this quantity not equal to 0 or is it equal to 0? Because this is going to tell us whether the matrix is invertible or not. So if I went 6 times 2 minus 1 times 5, really, this is exactly this expression AD minus BC here, right? I'm multiplying the two entries on the main diagonal, then I subtract the product of the other two entries. That's exactly what's written here. 6 times 2 minus 1 times 5. Well, what is that? It's 12 minus 5 if you work out the products, and that's equal to 7, which is not equal to 0. So, in other words, let's write it this way. Since this is not 0, that's really what this justifies, A is invertible. And using this rule up here, we now have a formula for the inverse as well. It's the scalar is going to be 1 over AD minus BC, which we just worked out to be 7, right? So this is going to be 1 over 7. So we can just write A inverse is equal to 1 over 7. And then now we need to fill in this part, right? So remember, how do you get from the 2 by 2 matrix to the part of the inverse down here? Just swap the two entries on the main diagonal and negate the other two. So if our entries are 6, 1, 5, and 2, just take the 6 and the 2 and have them trade places. And then put negative signs on the 1 and the 5. So this will be -1 and -5. And that's your formula for A inverse. Now you can leave it like this, but you are kind of leaving this extra scalar out front undealt with. And that you may choose to express your answer like this, and this is completely correct. But what we can also do is multiply the 1/7 into the brackets, or not into the brackets, into the matrix by multiplying each of these four entries by 1 over 7. So we'd have 2 over 7, -1 over 7, -5 over 7, and 6 over 7. So if I really wanted to know what all the entries of the matrix were, and you can argue that that's really the only way you do know what a matrix is if you know what all of its entries are, then you can write it this way. But both of those forms are fine. Okay, so what about the second example? Well, let's start by working out the product of -1 and 6 and 2 and 3 and doing the appropriate subtraction. So since -1 times -6 minus 2 times 3, right? So I'm taking this product minus this product, and that gives me this. Well, that's equal to 6 minus 6, which is equal to 0. And whenever that happens, if you work out this expression AD minus BC for a particular matrix and you get 0, then that means the matrix is not invertible. But we're talking about the matrix B down here. So our conclusion is that this matrix doesn't have an inverse. And there's nothing else you can say. So that completes the example. There's not much else to do. If you know it's not invertible, then you're not going to waste time searching for an inverse. Okay, so that's just an example of how we can deal with this in the case of 2x2 matrices. There's still lots of questions unanswered, right? What about the inverse of a 5x5 matrix? That could be incredibly difficult to find. So we're not going to deal with that just yet, but I do want you to realize that what we've done so far implies that the class of 2x2 matrices, their inverses are very well understood at this point. And another theorem that I'm going to mention says the following. It tells you how to build, or not tells you how, it tells you one way that you can build an invertible matrix if you have two invertible matrices already that happen to be of the same size. So let me tell you what I mean by that. So let's say A and B are invertible n by n matrices. So really what I'm saying here is that A and B are both matrices, they're both invertible, and they're both n by n for some choice of n. In other words, they're both square and they're the same size. That's what actually really matters. I don't really care what n is in this case. I just wanted to, this is the briefest way to say that these two matrices have the same size and are invertible. Well, what does the theorem tell you? It says the following. Then the product of those two matrices, A and B, and you know it's going to be defined because they're both n by n, so the product is well defined. AB is also invertible. And moreover, not only is it invertible, this theorem tells you how to get its inverse. So what I've written here is I've just said the inverse of the product A and B. So whatever I read on the other side of this equation will tell you how to get the inverse of this product. And it turns out you can just take the inverse of each of A and B and then multiply them, but in the opposite order. That's what this is telling you. And remember, we started with the assumption that A and B were both invertible matrices, so we already know that their inverses exist. The question is, does the inverse of the product exist? And the answer is yes, and this is what will do the job. So let's prove this, because it's not too hard to do. How do we do it? We need to check that if you take this matrix AB and you multiply it on the right by the product of B inverse and A inverse, you get back the identity matrix. Okay, so that's the first half of it. The other half is you need to show that if you multiply them in the other order, so if I multiply the same product but the factors will trade places, I have to get the 2x2, not the 2x2, the n by n identity matrix for this one as well. Okay, so let's start with the first one. And I really want to make something as clear as possible here, because this first step that I do might seem a bit weird. Note that you actually have three matrices. And you might say, well, there's more matrices than that, and you'd be correct. There's several matrices in this expression, but there's many ways of looking at it. I want you to look at this pair of brackets. I want you to see A and B as separate matrices that are being multiplied. And in this pair of brackets, the round ones here, we've just got some big matrix. It's not that there isn't two matrices being multiplied, but at this point, I don't want you to focus on that for the moment. I want you to focus on a pair of brackets with two matrices multiplied, and then another matrix over here. And the reason I want to do that is because I want to make it clear that I'm actually going to use the associative property here. Because with the associative property of multiplication, we kind of have this situation, right? We have two matrices multiplied in brackets, and then another matrix multiplied on the right. Think of this as like the C in this line here. And this property says I can shift the brackets over to the right and multiply these two first and then multiply the A on after. So I'm going to rewrite this expression so that the B and all of this is multiplied first, and then the A will be multiplied on after. So I'm going to use square brackets to make this clear. See how that's changed? So now these two matrices, the B and the B inverse A inverse, they're being multiplied first inside the square brackets, and now the A is being multiplied on after. Okay, so that's one application of the associative property. But now, if you look inside the square brackets, and at this stage now we will look at the B inverse A inverse as two separate factors. And actually we also have a B in here, right? Those three matrices, those are the ones we're going to apply the associative property to now. Because now you have something that very closely resembles the left-hand side of property 3 on the first page. We've got a matrix A, B, and C, three matrices, and the second two are multiplied first. Well, we can use this property to change it so that the first two are multiplied first. So we're applying the associative property again, but just to different matrices, to these three matrices now. So what happens if I do that? I'll have A, that'll stay the same, and now I'll have B times B inverse times A inverse, right? And the reason I want to do this is because now I can go somewhere with this, because I don't know what B is, and I certainly don't know what its inverse is, but I do know that the definition of an inverse implies that if you multiply a matrix by its own inverse, you get back the identity matrix. So this part right here is equal to the identity. So really what you have is just A, and I don't need square brackets anymore, because these just turn into the identity, so I don't need these round brackets anymore. So for the square brackets, I'll just use smaller round brackets. But these two brackets here should be matched up with these square brackets. And now I have A times the product of the identity and A inverse. Well, the identity and A inverse is just going to be A inverse, right? The identity multiplication by the identity does not change anything. So really, you just end up with A times A inverse. And now you can apply the same logic again. If you multiply A by its own inverse, it's going to turn into the identity matrix. So that's going to give us the identity. So that completes that line. And you see how we had to do two careful applications of the associative property, to really be careful about which matrices got multiplied first. But notice the order never changed, right? All we ever did was shuffle brackets. We never actually changed the order in which the factors were written. Okay, so this one we can do the same strategy, right? We've got a matrix, and then another matrix. Let's shuffle the product around so we can actually get somewhere. So I'm going to do the same strategy I did in the first line. I'm going to leave this B inverse out alone, and this is going to be multiplied now by A inverse times AB, right? So we had three matrices. These two were being multiplied first, and then the AB was multiplied on after, but now we're going to multiply the A inverse and the AB first, and then the B inverse will get multiplied on after. That's exactly what this notation says. And then, same as before, we'll do a bracket shuffle inside the square brackets. So we've got an application of the associative property here on these three matrices. So you're going to have B inverse times the product of A inverse A and B, and then just like before, it almost follows the format exactly of the previous calculations, but this A inverse times A will just be the identity. So really, you'll just have B inverse times the identity times B, right? And this product, the identity times B is just going to be the matrix B, so finally you just end up having B inverse times B, and then last step, right? Any matrix times its inverse on either side is just going to be the identity matrix. And then we finally get the identity matrix for our main result. So in other words, if I take the matrix AB and I multiply it by B inverse A inverse, where I can put B inverse A inverse on the right, or I can put it on the left. It works either way, we get the identity back. That's what it means to say that this is the inverse of AB. So that's how the proof goes. So that's why we can put our box down here to say that we've completed it.